Back in the 1930s, the Germans were researching chlorine trifluoride under the codename N-Stoff, or Substance N. At the time, they were interested in self-lighting flamethrowers for some crazy reason. That idea was scrapped because they had finally found something that was too risky for the Nazis. Chlorine trifluoride, ClF3, is the chemical equivalent of a bad hair day for safety manuals. It's a substance so feisty that even fire extinguishers hide when they hear its name. It's like the rebellious teenager of the periodic table, combining the charming qualities of chlorine and the audacity of trifluoride to create a sizzling cocktail of chaos. Rumour has it that when scientists tried to contain it, chlorine trifluoride responded with a sassy chemical eye roll and burst into flames just to show off. It's the kind of dangerous you'd see in old cartoons, the funny kind of dangerous that's anything but funny when it's real. Chlorine trifluoride is known for its extreme reactivity. It can react violently with a wide range of materials that are typically considered non-reactive, such as glass, concrete, sand, and even asbestos. Remember asbestos? Those fluffy carcinogenic fibers we covered the planet in, largely because they were so good at resisting fire? Chlorine trifluoride is all lol burn and sets asbestos on fire. In fact, it reacts with, well, pretty much anything really. Water? Air that's just a smidge too humid too. Humans? Remember, you're 2/3 water. Glass? Totes. Titanium? Lol. Cement? Say bye-bye to your flooring. Pre-burnt material? It'll resurrect the ashes and burn them again. Diamonds? Turns out, not lasting forever. But why is chlorine trifluoride so unhappy with everything else? Well, there's a branch of chemistry referred to as redox chemistry. That's short for reduction oxidation. Growing up in New Zealand, I learned Leo goes Gur. Loss of electrons is oxidation, and gain of electrons is reduction. Here in Australia, I was introduced to oil rig. Oxidation is loss, and reduction is gain. Of electrons, that is. I prefer the Kiwi version, but what we're talking about here is oxidation reactions. A molecule loses electrons to an oxidizing agent, commonly oxygen. Oxidation reactions create metal oxides, including rust. The breakdown of sugars in respiration is also an oxidation reaction, as is the breakdown of sugar in the Screaming Jelly Baby prac. But oxidation doesn't just look like one kind of thing. It's one of the most simple and common mechanisms in chemistry. And if you introduce a really strong oxidizer, like chlorine trifluoride, stuff gets wild. How does this happen? A few reasons, but it's largely to do with electronegativity, the attraction an atom has for a bonding pair of electrons. The second most electronegative element is oxygen, which is why it's so good as our go-to oxidizer. But coming in first and third in terms of electronegativity, well, that would be fluorine and chlorine. So a compound made by mashing the two of them together, it's one heck of a vicious compound. It wants those electrons now, and it's not shy about getting them. And it's not just the chlorine trifluoride you need to worry about. When it reacts, it can have some particularly nasty byproducts. Hydrochloric acid is one, and that's already a strong acid. But then we add hydrofluoric acid, which is neurotoxic. Unlike other acids that will simply leave you with a chemical burn, hydrofluoric acid will mess up your life even after you've cleaned it up. In 1994, a lab technician in Australia spilled hydrofluoric acid on his lap. He immediately followed robust safety protocol. But this acid starts working on damaging your nerves after it's absorbed into your system and can cause cardiac arrest. The technician died 2 weeks later. So how do you even handle something as dangerous as chlorine trifluoride? Really carefully. Specialized containers and facilities made of materials resistant to its corrosive nature, such as nickel or nickel alloys, are required. This adds to the complexity and cost of handling this hazardous substance. In the 1950s, whilst it was being researched as rocket fuel, a ton of it was loaded into a steel container to ship. As a safety precaution, they chilled the container with dry ice. but the container became brittle, cracked, and 1,000 kilograms of chlorine trifluoride was spilled onto the building floor. It reportedly burned through 30 centimeters of concrete and a meter of gravel beneath that. A gaseous combination of chlorine trifluoride, hydrogen fluoride, chlorine, and hydrogen chloride was formed, corroding everything it touched. In the event of a spill or release, responding to emergencies involving chlorine trifluoride is exceptionally challenging. Traditional firefighting methods are ineffective, as the compound can burn in the absence of oxygen, and water can react violently with it, producing toxic and corrosive hydrogen fluoride gas. Chlorine trifluoride has been considered for applications in rocket propellants and high-energy fuels due to its high energy content, but the associated risks have largely restricted its use. Despite its hazardous nature, however, it does have very limited industrial uses.
If you like this video, punch that like button. If you want to see more videos, smash that subscribe.